We are going to start our next section here. So Unit 5 is really all about kind of expanding some of what we know about the trig functions that we introduced in Unit 4. 5.1, the verifications, really focus on the Pythagorean identities, so the sine squared plus cosine squared equals 1 property. You'll notice that you use that pretty much in every single one of those verifications that we do. We're going to be moving on today to the next identity that we are going to be focusing on, which is called the sum and the difference identities for our trig functions. Unlike with the sine squared plus cosine squared equals 1 identity, this lends itself actually a very, very kind of utilitarian use in that it allows us to process angles that we would otherwise not be able to make heads or tails of. In particular, we could think of, say, trying to take the angle of something that is not on the unit circle, which on its own would be a borderline impossible task for us. With these identities, this is going to allow us to reframe certain angles that are off the unit circle in the context or in the terms of angles that we actually know, unit circle knowledge that we actually can access, so that we are able to kind of widen the angles that we are able to address with what we know about our trig functions. Normally, when introducing these, I did a little bit with the sine squared plus cosine squared. I have done it with pretty much all of the other kind of properties that we've looked at so far. I like to provide a quick kind of demonstrative proof that goes along with each of these, just to kind of convince you guys that, in fact, these are true, that they make sense, but also to kind of tie the memorization task to some kind of conceptual understanding. In this particular case, I feel that the conceptual understanding is actually kind of undercut a little bit, or does not necessarily help very much with the procedural task that I'm going to be asking you to kind of reproduce. And so to that end, we are going to be focusing on not how these kind of formulas come to be. You're just going to have to take my word. If you want to look up a proof, there are some pretty cool geometric arguments for why these properties are true. Not something we're going to cover within the scope of this class. Instead, we are going to focus on it's not quite a mnemonic, but it's basically like a mnemonic, of a little bit of a device to help us remember what is going on. So in this particular case, we are focusing on what happens when I take sine of, I'm going to label these as alpha plus beta. So sine of an angle that can be decomposed into the sum of two angles. We're going to compare that with what's going on with cosine of the same thing. Cosine of an angle being decomposed into the sum of two angles here. All right. Again, not mnemonic, but basically mnemonic that we are going to use is that sine is nice and cosine is mean. So sine is nice. Sine gets along well with other trig functions. Sine likes camaraderie. Sine likes to kind of mix and mingle. And sine isn't going to do anything shady with that plus. Addition is going to stay addition. We are not going to have to worry about any shenanigans with that. Sine of alpha plus beta can be instead reformatted to be sine of alpha times cosine of beta plus sine of beta cosine of alpha. And so notice sine mixes and matches, doesn't do anything with the plus. Cosine, on the other hand, is mean. Cosine's a jerk. Cosine likes to separate the room into two different kind of halves, and cosine only plays well with the cosines, does not get along well with any of the other trig functions. and also is particularly rude in that they are going to do some shady shenanigans to the plus sign that we have here. In particular, cosine of our decomposed alpha plus beta is instead going to look like cosine of alpha times cosine of beta minus sine of alpha sine beta. Now, of course, there are sum and difference identities. The difference identity really is just the sum identity. Addition and subtraction are the same operation. It's all addition. So we could think about, say, if we wanted to figure out what is sine of alpha minus beta, well, really, this is the same as sine of alpha plus negative beta. And so we could go through our sum formula, plug in negative beta, use even and odd properties in order to kind of iron out what that's going to look like. In particular, when we do, what is cosine of negative beta going to become using our even odd properties? Yeah, cosine of negative beta is the same as cosine of beta because cosine is an even function. So this is sine of alpha. Cosine of beta has not changed. But what's going to happen with sine of negative beta? The negative migrates outward. The negative comes out to the front. We get negative sine of beta times cosine of alpha. Or in the context of learning this as like its own kind of detached formula, notice that sine is nice, sine plays well with cosine, blah, 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 and it doesn't do anything to that minus. Minus is still minus. Conversely, if we do cosine of alpha minus beta, exact same thing. Notice again, cosine of negative beta is just cosine of beta. And so this first kind of piece here is going to stay exactly the same. Cosine of alpha, cosine of beta is unchanged, but sine of negative beta is negative sine of beta. That minus switches to a plus. Sine of alpha, sine of beta. Or cosine is mean. Cosine groups the sines with the sines, the cosines with the cosines, and then switches the minus to a plus. All right, let's check out the utility here. I'm looking at number 1, where we're being asked to evaluate sine of 105 degrees. Now, 105 degrees, is that an angle that we know? Is that a unit circle angle that we've learned? No, definitely not. So we can't just ask ourselves what is the y value that associates with this particular angle, even though that is kind of what we are being asked to. So our goal instead is to decompose 105 into two angles that we actually know. Now, it's important that it's angles that we actually know. So for instance, I've had some people try like 30 and 75. And we don't know what 75 is on the unit circle. We don't know anything about 75 on the unit circle. And so that's not actually very helpful to us. So trying to decompose this into two angles that we can actually use, what would be two good angles that we could decompose 105 degrees into? I think 45 and 60 is probably the easiest. Now, I say 45 and 60 is probably the easiest. There are others that we can do. Can anyone think of another kind of decomposition, maybe rather in terms of addition, maybe in terms of like subtraction that we could do to get to 105? Yeah, I like that as well. 150 minus 45 would also get us there. Notice the angles that we are using are all unit circle angles, right? 150, 45, 60, all of these are unit circle angles. And you could run this formula with the angles in blue, or you could run it with the angles in black. You'll get the same answer. It doesn't matter which one you do. The decomposition is the same, irrelevant. You just want to make sure that you're using the difference formula for one and the sum formula for the other. We'll go with the 45 plus 60. I think that one's the easiest one, kind of the most sensible one to come to. So we are looking at sine of 45 plus 60 degrees. So what do we know about sine in the context of our sum? Is sine nice or mean? Sine is nice, which means sine gets along well with others. And is it going to do anything shady to that plus sign? No, not going to do anything there. This is going to be sine of 45 times cosine of 60 plus sine of 60 times cosine of 45. We have gone from an angle that we can't deal with, 105, into a bunch of smaller kind of pieces, each of which we can evaluate. So for instance, what is sine of 45 degrees? Root 2 over 2. What is cosine of 60 degrees? One half. What is sine of 60 degrees? Root 3 over 2. And then what is cosine of 45? Root 2 over 2. Very good. I don't require us to simplify. You can box this answer, but in the interest of this, if we were to simplify, root 2 over 2 times 1 half is root 2 over 4. Root 3 over 2 times root 2 over 2 is root 6 over 4. They already have matching denominators. This is going to be root 2 plus root 6, all divided by 4. Questions here with our first example? Yeah. Either way is fine. I don't have a preference. Okay, now this decomposition process is pretty straightforward when it's in degrees. It's not too crazy difficult to do when it's in degrees. When it's in radians, figuring out the two angles that add to make the angle that we're missing can be a little bit harder. So let's take a look at number 3 here. This is cosine of 19 pi over 12. Let's just gut check ourselves really quickly. Do we know 19 pi over 12? Is that an angle that we're familiar with? No, we're not really going to be able to make a lot of headway by trying to tackle this kind of directly. But we want to figure out the decomposition here, and that can be a little bit tricky. One way that we could do this is we could convert this into degrees. But I try to give you methodologies that don't require you to convert from radians to degrees or degrees to radians, just because adding extra steps to this can increase the opportunity for error. Like, what if we do it wrong and then we're just, working with something horrible? Also, I think that there is utility in being able to work in just radians, because generally speaking, I am going to give you radians rather than degrees. That, as you have probably seen from what we've done in Unit 4. So what can we do here? This decomposition isn't necessarily easy. I'm going to give you guys a cheat. This is not something that I'm claiming like could work for every single angle, but if we can decompose the angles that we are looking at into unit circle angles that we know, this guaranteed is going to work 100% of the time, right? So it's a little bit of it comes with a little bit of a caveat to it, but if we are able to do this process, then this methodology should work, and otherwise it's either an angle that we should be able to just compute directly, or we were screwed from the get-go. There was no way that we were going to be able to decompose it at all into anything meaningful. And the way that we were going to do this, so we are trying to write this as cosine of two angles being added together. And I'm just going to tell you, go ahead and let's just set the first angle equal to pi over 4. You could do this with the degrees as well. If you want to set the first angle equal to 45 and figure out what the second angle would need to be, this will work. Yes. Is that a question? Or just, do you have a question?
How do you know if you're going for the sum of the angles or the difference?
That's a good question. We're going to address that here in a second. Yes, good question, and we'll take a look at that here momentarily. I'm telling you to just set it as pi over 4. Yeah, you get it from me right now telling you to do it. All right, so we are looking for this missing beta, and it'll work with degrees as well. So you could also set the first angle equal to 45 degrees, and you'll see, notice for the decompositions that we found, how 45 degrees was involved in both. Pi over 4 will be involved in all of our radian conversions as well. So we need to find this beta. How can we do this? Well, we know that pi over 4 plus this angle should be equal to 19 pi over 12. We just need to solve for this missing angle. So subtracting pi over 4 from both sides, I get that beta is equal to 19 pi over 12. And I'm going to rewrite subtracting pi over 4 as subtracting 3 pi over 12 to match the denominators. So minus 3 pi over 12, which again is just the same as pi over 4. This is 16 pi over 12, which we can simplify. That is 4 pi over 3. So Keenan, to answer your question here, the fact that this is a positive 4 pi over 3 means that we're going to use the sum rather than the difference. If it was a negative 4 pi over 3, we would use the difference. But we'll readdress that. We'll come back to that because that can lead to some confusion. All right, so this is equal to cosine of pi over 4 plus 4 pi over 3. What do we know about cosine in the context of our sum and difference? Nice or mean? Mean, it's going to mess around with the plus. It's going to move all the cosines to one side, all the sines to the other. We're going to get cosine of pi over 4 times cosine of 4 pi over 3 minus sine of pi over 4 sine of 4 pi over 3. What did we say is cosine of pi over 4? Root 2 over 2. 4 pi over 3, what quadrant does that live in? Third quadrant, so cosine of 4 pi over 3 is going to be negative 1/2. Very good. What is sine of 4 pi over 3? Or sorry, not 4 pi. Yeah, sorry, of pi over 4 first. Root 2 over 2. And now sine of 4 pi over 3. Negative root 3 over 2. I get that this is root 2 over 2 times negative 1/2 is going to be a negative root 2 over 4. Negative root 2 over 2 times negative root 3 over 2. Positive root 6, all divided by 4. Yeah, negative because what quadrant is 4 pi over 3 in? The third quadrant, exactly. So sine of a third quadrant angle would be negative. Yes, this is negative. It's not part of my square root. Yeah. It's hard to see even when zoomed in. I'll address that. Negative. Now let's say we solved for beta and we got a negative. Let's say hypothetically that the beta that we found was in fact negative 4 pi over 3. All right, obviously it's not. Let's say it is. What could we then do with this information? So one thing that we could do is we could say beta being negative means I'm adding a negative. Adding a negative is just the same as subtracting. So we could set this up as a difference. If you are going to set this up as a difference, is your beta going to be negative 4 pi over 3 or positive 4 pi over 3? So if it's negative, then we would have pi over 4 minus negative 4 pi over 3. Does that get us what we want if the beta is minus? That would be using that minus too many times. So either you're going to take that negative that's on your beta there and you're going to use it to say, well, this is going to be a difference. That's where the minus goes. It's alpha minus beta. Or you can use your sum formula, plug in that negative beta, and then use your even odd properties in order to work out what that is actually going to be. Either way is fine. I would probably go with because the formulas are pretty, I think, simple. Once you know one of them, it's pretty easy to convert to the other. I would probably go with just doing the difference formula. But that negative beta, make sure if you use the difference formula that your angles are all positive. Because that negative that you found is going into the difference part itself. If we were using the sum formula, you would use negative beta. If you're going to use the difference formula, use positive. All right, I'm going to give you guys, we'll say 5 to 10 minutes. Take a stab at 2 and 4. Same idea. First, figure out what the decomposition is going to look like. How can you decompose this into two angles that we know, and then figuring out kind of the machinery. Hold on to that. No, not on the. But also, you don't have to like. Is that for like simplifying? Yeah, you also don't have to simplify. Like if you circle your answer like once we got like here, that would be perfect. So if you're worried about this. That looks good. Thinking, how can I write 165 as two angles that I know together? And if we're struggling to figure out what those two angles are, you can always have 45 be the first of those circles. Kind of similar to how pi over 4 is that. Yeah. So you also could do it as a difference. That's fine. You could come up with two angles and subtract to make 165. And there's nothing wrong with that. Just you could. This one was more just like once think of ones, and this was not 160, but just 60. So 45 plus 60 was 105. And this is just kind of like, let's just think about like ones that it could be. But if you want like a surefire way, kind of similar to what we did down there, where you just set the first one to or you can always just let the first one to 45, and you should align the second one is an angle that we also. So it's kind of similar because pi over 4, 45 degrees are basically the same thing. Yeah. Yeah, we want to use numbers on the units because like if we did like 20 degrees and 145 degrees, there's nothing wrong with those. Like that certainly does compose. It's just once we break it apart and we're asking the question, what is sine of 20 degrees? We don't have an answer yet. So we want to use ones that are like for us that can actually answer that question. Yeah, good question. You're gonna hand it in. Okay. Nope, either way is fine. Yep. Especially because like both of these are units, like all of these are units of one, so just use whichever ones feel easiest for you. Yeah. And you don't even need to find like multiple. I just showed you that you can find multiple and any of them work as long as you're. Cosine of 120, what quadrant is 120? Second quadrant. And so what do we know about cosine in the second quadrant? Negative, so we need negative root 3 over 2, but otherwise that would be. Yep. Although actually 120, is it going to be root 3 over 2? X value would be 1.5, yeah. So it's flipped, but ultimately because it's addition. Yeah, it's the X value. Although. Yeah, exactly. Okay. Yeah. You could do difference. So you could either do the sum of pi over 4 and negative 2 pi over 3, or you could do the difference of positive pi over 4 and positive 2 pi over 3. And that would
So it doesn't really matter.
They're basically the same. Yeah, they're basically the same. It was like the same answer, yeah. Yep. Just make sure you don't do the difference formula and plug in the negative theta, because that will be wrong. So either do the difference formula and plug in the positive, or the sum formula. Anyways. You could set it up straight away if you want to. Just make the note that you'll use difference formula here. You could also solve for B. You'll end up with a negative value for B, and then you could use the difference formula once you notice that you have a negative value. These have the same reference angle. Right, this is like all 15-degree reference angle or 75-degree reference angle. So what we're seeing is the same reference angle but in different quadrants, which is why they're very similar in terms of the numbers. But pretty much they're all going to be very, very similar to this. They're not all exactly the same. Like negative root 2 plus root 6 is going to be slightly different, but they're about they all have very similar parts. And it's all because we can only really use this to figure out those 15-degree, 75-degree reference angles. That's really the utility that we're getting.
So for you said to use pi over 4.
I would use pi. Yeah, I would use pi over 4. Yeah, of course. All right. Let's take a look at number 2 here. So this was cosine of 165 degrees. What was a decomposition that we used here? I like 120 plus 45. Did anyone use anything else? I think Nikaya found another one. Nikaya, what did you find as well? 210 minus 45, which also would have worked. That would have also worked. 135 plus 30 would have also worked as well. There are an infinite number of these that we could come up with. They'll all work. It's all fine. Okay. But we can run with 120 plus 45. I like that. Cosine is mean. So cosine is going to group the cosines. It's going to switch the plus to a minus. This is cosine of 120 times cosine of 45 minus sine of 120 times sine of 45. What is cosine of 120? Negative 1/2. Negative because what quadrant are we in? Quadrant 2. Very good. Cosine of 45, root 2 over 2. What is sine of 120? Positive root 3 over 2, and then sine of 45, root 2 over 2. Sorry, brain lagging a little bit there. And so we get negative root 2 minus root 6 over 4. All right. And then lastly, for number 4, we are looking at sine of negative 5 pi over 12. I had a student in my first period ask me if we could first find find a coterminal angle and then do the decomposition. And yeah, of course, that would absolutely work. Nothing wrong with that. But also we can just do the decomposition directly. What do I say to always set alpha to? Let's just set it to pi over 4. And what is the beta that we found if alpha is pi over 4? Negative 2 pi over 3. So thinking like negative 5 pi over 12 minus 3 pi over 12 is going to give us negative 8 pi over 12, which does in fact simplify down to negative 2 pi over 3. So that negative either is going to tell us one or the other. It's either going to tell us that our beta is negative, which is fine, and then we'll use the sum formula, or it tells us to use the difference formula, in which case the beta is positive. Either way, we should get that. We're looking at sine of pi over 4 minus 2 pi over 3. Be very, very careful here that we are in fact doing minus 2 pi over 3. I also had some people who looked at this and said, well, if I'm starting at positive pi over 4, then I know I'm going to need to subtract in order to get here. And so they set this up initially as a difference and then found a positive beta. That's also fine. There are a lot of ways to do it. Just make sure that you don't end up plugging in the wrong style of angle into the formula, right? You don't want to subtract twice and end up adding a positive, right? So in this case, this is sine of pi over 4 times cosine of 2 pi over 3. I'm using the difference formula here, but you certainly could use the sum. That's totally fine. Minus sine of 2 pi over 3 times cosine of pi over 4, which is going to be root 2 over 2 times negative 1/2 minus root 3 over 2 times root 2 over 2. I get actually the exact same thing that we got for number 2, negative root 2 minus root 6 all over 4. questions with our sum and difference identities here? Yeah, Bryce. Because if we set alpha to be pi over 4, we're just going to set that to be pi over 4. And the equation that you get is that pi over 4 plus beta is equal to negative 5 pi over 12, subtracting by pi over 4 on both sides in order to solve for beta. Yeah. Good question. Other questions here? Yeah, Sumira. Yeah. Yeah, so sine of, well, I can show you here. So this would be sine of pi over 4 plus a negative 2 pi over 3. Since we have plus here, we're going to use our sum formula. So this would be sine of pi over 4 times cosine of negative 2 pi over 3 plus sine of negative 2 pi over 3 times cosine of pi over 4. What's going to happen with cosine of negative 2 pi over 3 because cosine is even? Yeah, exactly. That's just going to be the same as cosine of 2 pi, or of just regular 2 pi over 3. And then what's going to happen with the sine of negative 2 pi over 3? It's going to migrate out, and so we get minus sine of 2 pi over 3 times cosine of pi over 4. And at that point, we are matching what we have here. Yeah. Which is kind of a consequence of the fact that actually our difference formula is the sum formula, just with even and odd properties applied to it. Yeah, that is actually, it's not a coincidence. That is part of the derivation, is that the even and odds give us the difference formula. Yeah, which is cool. And it gives us some flexibility in how we do this. All right, so that's sine and cosine. Tangent, we could actually do tangent as sine of alpha plus beta over cosine of alpha plus beta. And in fact, a really good bonus question might be something along the lines of like, show that the formula that we're actually going to use for tangent is equivalent with the sine of alpha plus beta over sine of over cosine of alpha plus beta definition. That would be a fun one to use. Either like a challenge set problem or like a bonus question on a test. Both of those could be kind of fair game there. But we're, again, just going to kind of stick with the not looking too hard at the derivations. In this case, looking at tangent of alpha plus beta. Tangent is sine in the numerator, cosine in the denominator. And so what we see is kind of a little bit of niceness on top and a little bit of meanness in the denominator. This is going to be tangent of alpha plus tangent of beta divided by 1 minus tangent of alpha tangent of beta. Notice in my numerator, the plus, because I'm doing the sum, stayed a plus, but in my denominator, the plus turned into a minus. Just to highlight, this stayed the same, but then switched down here. Likewise, if I were to do tangent of alpha minus beta, again, the numerator, and you could do this with even and odds as well, and you would get the same thing, over 1 plus tangent of alpha, tangent of beta, where now notice minus, minus, and this is suddenly a plus. So numerator is nice in as far as the plus will stay a plus, the minus will stay a minus. The denominator is mean in that the plus will switch, the minus will switch. But otherwise, it's exactly the same. Now, one of the really nice things about using pi over 4 as one of our thetas, just right off the gate, is that tangent of pi over 4 is the easiest tangent value to use to kind of compute. What is tangent of pi over 4? Yeah, which is going to simplify down to 1. Yeah, root 2 over 2 divided by root 2 over 2, number divided by itself is just 1. And so this tangent of alpha, that tangent of beta, or tangent of alpha in both the numerator and denominator, generally speaking, are just going to be 1, which is kind of nice. Not always, but often with what we will see here. So for instance, let's take a look at number 5 here. We are trying to figure out what is tangent of 13 pi over 12. Let's again let alpha be pi over 4. I'll give you guys like a minute. If alpha is pi over 4, what is the beta going to be here? What did you say? 10 pi over 12, which is going to simplify down to 5 pi over 6. Very nice. Very, very nice. Subtracting 3 pi over 12 from both sides. And so this is equal to tangent of pi over 4 plus 5 pi over 6. And so we'll use our sum formula here. This is tangent of alpha plus tangent of beta divided by 1 minus tangent of alpha times tangent of beta. We said that tan of pi over 4 is 1. What is tangent of 5 pi over 6 going to be? So sine of 5 pi over 6 is almost. That would be if it was 2 pi over 3. That would be the pi over 3 reference angle. So sine of 5 pi over 6 is 1/2 divided by cosine of 5 pi over 6, negative root 3 over 2. Clean that up a little bit. You should get negative 1 over root 3. You could also write this as negative root 3 over 3. Either way is fine. So close with the root 3, but the reciprocal in this case, the x and the y flip-flopped. And so we get that this is 1 plus tangent, well, that's minus 1 over root 3 over 1 minus 1 times negative 1 over root 3. I'd honestly probably be fine if you left it like that. Yeah.
Pi over 4.
So pi over 4 is where sine and cosine are the same. And so if we do sine divided by cosine, we get 1. So we could box this. I'd be okay with that. But this actually cleans up not too badly. For instance, rewriting the 1 in both the numerator and the denominator as root 3 over root 3. You should end up with root 3 minus 1 over root 3 plus 1. and either way is fine. I'm perfectly happy with, even though I probably shouldn't be, I am perfectly happy with this. I am also perfectly happy with this. All right, questions with tangent? Yeah, done. If you match the denominators in the numerator and the denominator and change the 1 into a root 3 over root 3 to actually do out the addition, do out the subtraction, and then simplify your giant stack of a fraction that you get, you should end up with root 3 minus 1 over root 3 plus 1. I would try it out if try simplifying that as a fraction. I will leave that as an exercise to the reader to figure out how to simplify from here to here. Good practice, especially with some of the identities that we'll have to do. All right, if we look at the back here, 7 through 14, these are fairly straightforward. So these identities are obviously not just in one direction. We have an equal sign. We can go in either direction. Oftentimes the difficulty with this is identifying which machine we're using. So are we using tangent? Are we using sine? Are we using cosine? And then just figuring out, okay, are we using the difference or the sum for these particular things? So for instance, looking at number, let's take a look at number 7 here, where we are looking at tangent of 48 degrees plus tangent of 102 degrees divided by 1 minus tangent of 48 times tangent of 102. Okay, so first and foremost, which function is this going to collapse into? Is it going to be sine, cosine, or tangent? Okay, tangent is kind of a nice gimme in that it only uses tangent. Okay, so this is going to be tangent, and this is either going to be tangent of 48 plus 102 or tangent of 48 minus 102. Which one is it going to be? Plus, and how do you know that? Yeah, so whatever that numerator plus or minus is going to match the inside of our tangent here. This is in fact going to be tangent of 48 plus 102, which would be tangent of 150. And we go from angles that we don't know, 48 and 102 degrees, down to an angle that we know. 150 is actually the same thing as 5 pi over 6. We already evaluated this. This is -1 over root 3. Okay, the tangent one's not too bad. Sine and cosine's a little bit trickier of just like determining whether we're looking at sine versus looking at cosine. So for instance, if I'm looking at number 8, where we are told that cosine of 300 degrees times cosine of 15 degrees, we're trying to evaluate, minus sine of 300 times sine of 15. Now, first and foremost, do we know what sine and cosine of 300 degrees is? Is that a unit circle angle? 300? Yeah, 300 actually is, The problem is if we evaluate that right now, we're going to be left with these sines and cosines of 15, and we don't know how to deal with those. So just because we can simplify the 300 there doesn't mean that makes it easier. It actually makes our task a little bit harder. Looking at this, which of my functions is this representative of? Is this the result of niceness or meanness? This is cosine, so this is going to be cosine of. And is this going to be a sum or a difference? This is going to be a sum because it does the opposite of what we see here. The minus here actually indicates that it was a plus that then switched to a minus. Which then just unit circle knowledge, root 2 over 2. Quadrant 4, reference angle of 45 degrees, root 2 over 2. Yeah.
Wouldn't that be negative 2 squared over 2?
Quadrant 4, x is positive in quadrant 4. So if it was sine of 315, yeah, it would be negative, but in this case, positive. Any questions here with 5.2? Because the rest of these, 11 through 14, really 9 through 14, these are all just the same. It's just collapsing. Yeah. So if we look at the sine kind of decomposition and the cosine decomposition, notice that the sine decomposition, the sines and the cosines are kind of grouped together. We've got sine, cosine plus sine, cosine. Whereas for cosines, the cosines are all together in one, and then it's the sines. So that's how we can kind of look at this and say, well, which of those do I have? Notice here how I've got cosines on one side, sines on the other side. That tells me that it must have been cosine originally. And then the fact that it was cosine means that that minus must have originally been a plus because cosine is mean and it switches them. Yeah. So start with the is it sine or cosine and then worry about the plus minus would be my advice for order there. Yeah. So the second worksheet that I handed you guys, the second sheet, the 5.1, 5.2 review, that is taking place of a Pearson, that in tandem with the worksheet that you guys had that's due today, taking place of the Pearson for that will go for this quiz that we have on Thursday. That being said, I have had requests for a 5.2 Pearson that is just purely for practice, just to kind of get used to some of these identities. And so I am going to be creating and uploading that. It's not going to be for a grade. It is purely for just extra practice with it. So that will be a resource if you'd like to take a look at that. Not uploaded yet, but I will upload that probably at some point during tutoring that I have this afternoon. And then other thing that I wanted to kind of mention, I said that the worksheet due at the start of class, if you are finished with your worksheet that was due today, you go ahead and bring it, put it up here on the podium. If you are not done, you've got 25 minutes. So you can not done. Okay. here and then here. So which side would you say is the more complicated? I absolutely agree. So what do you get when you write that in terms of signing?
I mean, it's so
Yep.
Yes, it is.
All divided by Yep. Okay. What would we do to actually like do out this addition? What do we need to do? Match the common denominators. My hint for you here will be, it's going to be very tempting. You're going to get like a sine squared plus cosine squared. Very tempting to combine those to make it one. But notice that you're eventually going to need to take this single fraction and split it apart into two things. So if you don't simplify, if you don't combine those into one, leave them there, do the multiplying by the reciprocal thing, and then try splitting the fraction and see if you can see where you're going. Yeah, of course. Yes.
I got.
When you multiply by the reciprocal here, is it going to be sine cosine over 1? What is the reciprocal of this? No, it's going to be this, like this. What is the reciprocal of that? It's 1 over sine cosine. So you're multiplying, it's the reciprocal of this. So it's just this, but flipped upside down. It's not multiplying into the numerator, it's multiplying into the denominator. You could write it like that, but I would honestly just leave it as 1 over sine times cosine. Because that'll multiply, you'll get a sine squared here and a cosine squared here. And then just try, you'll get a fraction. That's like sine squared plus cosine squared over sine squared cosine squared. Try splitting that fraction. Just to explode it out. So this is just the reciprocal. So you multiplied by the denominator. You need to multiply by the you need to multiply by the reciprocal. By the reciprocal of this. Yes, exactly. And then cancel up here. It's not going to cancel. You need to first split your fraction and then do this. Yeah. So split your fraction and then. Yeah. So try multiplying by the reciprocal and see if they would cancel. Because you've got fraction in your numerator divided by something in your denominator. Dividing, when we take a fraction, divide it, you can either think of multiplying that into the denominator, or you can think of doing the reciprocal of it and multiplying it to it. Yeah, exactly. Exactly. Yes. Just let me know.
Yeah.
Yes, that'll be due Thursday.
Okay, so this is the numerator.
Yeah, it's on Thursday. Thursday.
So this is one.
Test is, I don't think the test is on Friday. I think the test says it's on like Tuesday of next week or something.
Yeah, it's on.
Or does it say Wednesday?
Oh, I
Okay.
thought you
Yeah,
said-
that was my game plan this week. I like to have them after my tutoring sessions. So that was my game plan. That's it. Does that end up working out? We do. Stay Tuesday. What day where we maybe start? Cool. Okay, we'll start polar coordinates and then we'll do our test. For the test.